It's 11:10, so we can go ahead and get started. The topic of this particular session is methods for optimizing vector modulation, and we're talking about IQ modulation here. And also I'll talk a little bit about alternative or some more modern methods that are emerging that apply to some applications, not all, but in terms of IQ modulation. But we want to be able to optimize that signal because vector signals made up of a phase angle, of course, and a magnitude that is translated from those polar coordinates to the rectangular coordinate system of IQ. So there's a deterministic link there between those two, and we'll probably keep that in mind as we go through this. The IQ modulator, fairly simple in basic structure, although a little bit difficult to optimize, and that's what we're going to talk about here in the coming slides. But we have an LO input that's shared between two mixers. We split that and shift one 90 degrees from the other. That gives us, we call that in quadrature, the two signals are in quadrature, providing us with two RF signals, RF1, RF2. And here's our I and Q input, which of course are our analog baseband signals that represent our vector modulation when combined in this method. And out comes our IQ input. This goes on to the RF for upconversion, filtering. But here there's quite a bit that can go on within the IQ modulator that we need to really consider and optimize. The first thing, and probably most important, as signals become more and more wideband, the effect of frequency response of the IQ modulator has some dramatic effects on our system performance. If we have a IQ modulator that has a frequency response that looks something like this across a 4 gigahertz frequency span, even if we're looking at a 200 megahertz channel in here, you can see there's quite a bit of variation in just the magnitude. And that's what this particular chart shows, is magnitude only. But there's of course the other component to consider, and that's the phase distortions or group delay. And it'll have a similar frequency response as well. We need to be able to mitigate the effects of this frequency response through adjustments within the IQ modulator or the I and Q baseband files themselves. So here's a representation, I hope you can see this, of a multi-tone signal. We have 20 tones here spanning 2 gigahertz. I guess maybe I should qualify some of the bandwidths here in that a lot of commercial communication systems, we're talking 20 megahertz or maybe up to 160 megahertz with some wireless LAN technologies. Of course, in aerospace and defense applications where you're using radar or you have a satellite with multiple transponders filling up a very large segment of bandwidth, these kinds of issues are become even more acute with the extension of those bandwidths. So radar, electronic warfare, satellite, all use bandwidths or need to be tested and characterized in bandwidths in the gigahertz range. So of course, Agilent has products that can generate and analyze these as well. But getting back to the flatness, both amplitude and phase, and of course phase is hard to visualize here, so we're going to focus a lot on amplitude. And you can see the roll-off of the frequency response of our system across the 2 gigahertz bandwidth. So what do we do to mitigate that? We need a nice flat bandwidth. We need to rid ourselves of those phase distortions. Well, in what I call the classic methodology for getting rid of these is where we take the signal, the IQ waveform in a digital file, and load it into an arbitrary waveform generator. We can upconvert that, of course, with a signal generator that has a wideband arbitrary IQ modulator within it, and then take a spectrum analyzer or some other digitizing platform. Could be an oscilloscope. Spectrum analyzer, of course, gives us the best dynamic range, and correct the signal. We make measurements, narrowband measurements all along the the bandwidth of interest. We pre-distort or correct or calibrate our waveform, and then we download that corrected waveform into the arbitrary waveform generator. And that provides us with the ability to pre-distort that signal and achieve a very flat magnitude and phase response across the entire bandwidth. Here you can see we're down to less than half a dB across a 2 gigahertz spectrum with these multi-tone signals. And of course this can be applied not just to multi-tone signals, but also any kind of digital modulation or vector modulation. Well, is there a better way to do this? And yes, of course this is kind of a little bit of a commercial. We have a signal generator, MXG, that does all this correction in real time. And it uses a couple of different ways to do that. There's a fully temperature compensated calibration done at the factory, of course, so it knows exactly the operating point of the entire block diagram of the system at any particular temperature or operating condition. And in this case, so we can apply some baseband processing to flatten the spectrum across 160 megahertz of bandwidth in real time. So there's no more changing or altering the waveform file. It's all done in real time for you within the system. And it's done both at baseband. I won't dwell on this slide, but we have baseband corrections that are calculated at boot up or when a cal is run, and an RF correction. And these are convolved with one another in order to get that flat phase and magnitude response. So, and I guess it's good to note you can also turn this off. You do give up a few microseconds, maybe tens of microseconds of switching speed when you invoke the real-time corrections onto your waveform. So that's the little bit of a trade-off, but of course the flexibility we give you is to be able to turn this off if you have other means for correcting your signal or you don't need this kind of accuracy. Any questions so far with that? So I'd like to jump into some of the imperfections in the IQ modulator and how we can mitigate those issues. And the first one you see usually is an LO feed through. And of course it's caused by the paths being not identically matched in terms of a DC offset between our I and our Q signals. So the DC offset between the I and Q allows some of the LO to bleed through to the RF signal. Now there's a couple of things we can do. We can apply some pre-distortion. That's similar to what I just talked about, where we go in and in this case, we take the waveform file, we take a tone 180 degrees out of phase with our LO, and we place it right at the LO in order to kind of like noise canceling headphones to take that or reduce that effect. We can also adjust the I and Q path DC offset level. And here it is visually, of course, the I signal, a little bit of a voltage difference between the Q at the input. And of course, here you can see the difference. DC before offset adjustment, we got a 55 dBc LO feed through. After a DC offset adjustment within the signal generator, we get minus 66. And of course, we could reduce this more if we used a pre-distortion technique to put a tone in here to cancel this particular tone. That's another method that you can use. Of course, most modern, including Agilent's signal generators, have this capability to adjust DC offset. The PSG here, I'll just mention very quickly why you see two screens here, is the PSG actually has two IQ modulators internal to it. One is a narrowband that operates with the internal arbitrary waveform generator, and the other one's a wideband IQ modulator that can accommodate signals up to 4 gigahertz, between 2 and 4 gigahertz, depending on where in the spectrum you want to modulate these signals. We can adjust either path, either IQ modulator path. And of course, like I mentioned, most modern signal generators have this capability, but a lot of people aren't aware that you have the ability to optimize your signal in this method. So here's the effect of using a pre-distortion. Here's the minus 55 LO feed through again. And if we put a tone 180 degrees out of phase with the LO, we can get it down to minus 73 dBc. So let's move on to some other LO, or not LO, but IQ modulator imperfections that you may encounter. And one of those is quadrature error, where the signals that are split from your LO are not exactly 90 degrees phase difference between them. So that gives you a imperfection that hits the mixers, and mathematically and deterministically you can figure out exactly what kind of image or distortion tone that you're going to get at this particular frequency. Won't go through the trigonometry here, it's pretty straightforward, but as you have an error term here in your phase, you develop an unwanted image out here due to your quadrature error. And of course, once again, this is a PSG, but this applies to any modern signal generator. You do have that adjustment to adjust that I and Q quadrature within your signal generator. Another imperfection that you'll see within the IQ block of your signal generator is gain imbalance and timing skew. And this, of course, is where you have a delay between the I and the Q signals as they approach the mixers. So you have a difference in time called a timing skew, and you may also have a gain imbalance. One may have more gain or loss within the path than the other. So this is something that signal generator manufacturers take very seriously when they design and lay out their signal generator in order to make sure those paths, the I and the Q path, are identical. But if they're not, you're resulting in what's called IQ images, and I think I have a picture of that here. Here you can see kind of a curve, kind of a bird or bat wing effect of the images showing up here in this multi-tone signal. We're using 100 megahertz of bandwidth to illustrate this, but it's hard to see, but you can see a lot of these images or tones showing up there. Basically, yeah, similar to this. Now we can adjust that gain balance and timing skew again within our signal generator. Let me go back. Sorry about that. Here within the user interface. So once again, we can reduce those images and across the entire modulation bandwidth. And here, when we make that adjustment, we've gone from images up to 23 dBc all the way to minus 40. All the way down to minus 40. And here's another representation of that where we've suppressed the upper tones, and you can see all of these distortion products where we've misadjusted the timing skew by 400 picoseconds. So it's actually quite a bit. And you can see how much the effect of these images. So we've gotten rid of the desired tones, and here we can just see the distortion products. If the skew is properly adjusted, you can see that these distortion products disappear. So any questions about some of the adjustments that we can make and the different anomalies you might encounter with the IQ modulator? Okay, let's talk about IQ modulation, different techniques for IQ modulation. You can see, once again, we have an analog IQ modulator here, and you can see some of the distortion products and effects of the analog IQ modulator in the picture. Or maybe you can. It's a little washed out, but there's a lot of images in there from all the different imperfections that I've listed before, whether it's timing skew, gain imbalance, DC offset. You know, they give you these effects. When you go and you do the modulation in a digital method, and classically that could be done in the IQ waveform. So you do a little bit of extra math in the software, and then instead of creating two waveforms with I and Q, you basically create an IF waveform, basically, you know, frequency and magnitude that you can put directly into or load directly into an arbitrary waveform generator, and outcomes instead of from a two-channel arbitrary waveform generator, you have IQ, you have one channel that has the IF signal coming out of it. So it's basically doing the IQ modulation in software stored within your waveform file. Simple as that, but that's not often convenient. It has some problems in upconversion. You have a lot of insertion loss when you try to mix this up. But what you do have at the IF output is a very clean spectrum without all these sins of the IQ modulator. These have gone away. And as I mentioned, this is done non-real time as what I've just described. And that's a little inconvenient. So what if we could do IQ modulation digitally or with math in software in real time? That's really where we want to get to. And here's an example, of course, of no in-band images, no feed-through. So, and also we can flatten. You still have the effect of some of the magnitude frequency response here, but the other distortions of the IQ modulator are disappeared. But let's get to this particular slide where we've described this analog methodology here already, and we just talked briefly about doing this in software, creating the waveform file that's already done the IQ modulation mathematically. What if we could do this in real time? There's a couple benefits to that, because you can interpolate your sample rate here within the arbitrary waveform generator perhaps to save you some waveform memory that you can't do with this methodology. So, and we can do this, of course, with the Agilent M8190 arbitrary waveform generator. We have the ability to do that IQ modulation directly within FPGA, right here. And we can lower the sample rate of the I and Q data and upconvert basically, or interpolate the sample rate up in order to get the full IQ modulation bandwidth. We also have a DDS engine, which I invite you to come over to the booth and talk to me about, which gives you a lot of flexibility in creating different scenarios within your waveform on top of your IQ modulation file. Okay. I think we'll leave it at that because I'm out of time. Are there any questions? Okay, I welcome you. We have this set up over in the Agilent booth, and like to talk to you about it further.